This is a Chapter 6 pre-class lecture on biodiesel. So we did our biodiesel lab this week, and we saw that biodiesel can be made from fats and oils, which are called triglycerides. Waste cooking oil is an excellent source of oil to be used. Therefore, this wasted cooking oil is not taken to a landfill, but is used to produce a fuel. Biodiesel molecules contain a hydrocarbon chain with anywhere between 16 to 20 carbon atoms. And they usually contain at least one double bond. And then biodiesel molecules also contain what we call an ester functional group, which we're not going to go deep into. That's a concept that would be further elaborated on in a class like organic chemistry. And then when you react the oil, the triglyceride, with an alcohol like methanol, we can also use ethanol like we did in our lab this week, as well as a base, sodium hydroxide. You produce your biodiesel and a side product called glycerol. And so looking at the structural formula for our biodiesels, this is called our alkyl portion of the biodiesel, which are the long hydrocarbon chains. And so looking at the structural formula for our biodiesel, having the long chain alkyl groups plus the carboxyl functional group, and then depending on whether we use methanol or ethanol, here they use methanol, you'll also get either a methyl group or an ethyl group on the end. In this case, a methyl group, because methanol was used. So that's where that group comes from. If ethanol would have been used, then this would be an ethyl group, CH2CH3. So that methyl group would be called our R prime group, whereas the alkyl portion, that's our R group. So this is a transesterification reaction. And so therefore, taking into account the structural formula for the biodiesel molecule, so what we predict that the heat that's released per gram of the biodiesel burned is higher or lower than that of octane. Well, one thing that's true about biodiesel, because it's made from methanol or ethanol, which are alcohols, it's oxygenated, just like ethanol. So therefore, it will release less heat per gram than octane. And so part B, if instead the comparison were made on the basis of 1 mole of biodiesel, which would release more heat if burned? Well, in order to determine this, we would need to know the exact molar mass of the biodiesel. So that we can convert the grams of biodiesel into moles. And so is it more useful to make comparisons about the energy released for a fuel in joules per gram or joules per mole? Well, joules per mole is more useful than joules per gram. And the reason why that's true, let's say you are doing a particle per particle comparison. But if you are doing a mass comparison, the per gram measurement is more useful. So it just depends on what type of measurement you're doing. If you're trying to compare particle per particle of octane to biodiesel, then you want to do a mole, joule per mole comparison. But if you're doing a mass comparison, then the joules per gram measurement for delta H would be more helpful. And so here you see that ethanol is oxygenated, just like biodiesel is. And that's what causes it to have a smaller heat of combustion than octane. And that brings us to the end of our Chapter 6 lecture on biodiesel.